In my last video, we talked about kind of developing an understanding of what a transfer function is. In this video, I hope to kind of give some more insight into how we can use transfer functions to predict different things about our system. In particular, we're going to do another stability analysis similar to the von Neumann stability analysis performed in, I believe, my first series. I think the second video performs stability analysis. Maybe it's the second series, first video. I don't know. Either way, this time, instead of working with the more numerical methods, and we're going to work more analytically, using the Routh criterion to develop a modularity of stability for any sort of process system. So we're going to start out by talking a little bit more about control techniques. We're given a process transfer function. We're told we're dealing with a system of 3 tanks in series, and we're given a process transfer function to describe the process. So we're told that we're working with a proportional only controller on this system. And so the first thing that we're going to do here is actually start to develop a control block diagram for this system. So this is a fairly common schematic in control engineering. And what we're going to do here, we're going to start out with this guy. And this is going to be our input into the system. I'm going to call that RS, which is just how my textbook denoted it. And then we're going to have it go through kind of the modulator there, that node. And that node is actually going to be ending up comparing it to the set point. Sorry, this should not be RS. This should be our set point. So let's call it set point in S domain. And then we're going to compare it to the measured value. And that'll give us an error in the Laplace domain. And then we're going to go through our first block here. And this is going to be our GC block, so our controller block. And what this is going to go ahead and do is modulate that error for us. We're told we're given a proportional only controller. And so usually what we do is we write the control inside the blocks. So that's going to be KC. And then we have a process gain here that's going to go through next. So this is going to be the gain of the process. And we're told that for this system it looks something like this. It actually has it as K, but I'm going to write it as KP so we don't get confused. Tau S plus 1 cubed here. And so we can call this our input term, US, or process input that's already been modulated by control. So then what's going to come out is going to be our output. So this will be YS. However, we are going to need to send some sort of signal back. And that's what's going to happen in our measurement function here. We're just going to use a measurement signal of 1 for right now because the problem doesn't specify what the measurement or sensor is actually doing here. And so then we're going to send that back up here to be compared against our set point again. And that's the control block diagram for this third order system. So what we're going to do next is we're going to determine Okay, so what values am I limited by in terms of system stability with my controller gain value, that KC value, sorry. So, um, often what we do here is we go ahead and define a closed loop gain for the system as a function of S. And without getting too deep into this derivation, what we generally quantify this as is the gain of the process times the gain of the controller over 1 plus gain of the process times gain of the controller. And so we're actually given all those values now, so we can go ahead and plug these in here. We know the gain of the process is going to be my process constant over tau s plus 1 cubed. And then I'm going to multiply that by kc, which is my controller gain. That's going to all be over 1 plus, again, process gain times controller gain. And so we can go ahead and start to simplify this. Let's go ahead and try this. So this will be kp kc over tau s plus 1 cubed, and then we're going to multiply by 1 over kp. This should be what 1 over 1 plus kp kc tau s plus 1 cubed. And so then when we go ahead and do that fraction multiplication across, what we end up with is kp kc over tau s plus 1 cubed plus kp kc here, because that'll cancel off the bottom. All right, so now we've gone ahead and defined the closed loop gain of our system here. And so what we're going to do next is, just realized that this guy's a little bit in the way. There we go. What we're going to go ahead and do next is attempt to define our limits of stability for the system. We're going to make the assumptions that tau and kp are values that we cannot change. However, we do know that the denominator of this equation is the characteristic equation of our control scheme. And what that means is that wherever the roots are real, we have a stable system. So, we could attempt to try and find the roots that would make the system work. However, Routh Horowitz were two people that went ahead and defined a way that we could use this, that we can quantify these polynomial roots and determine whether our system is stable or not. And so what they did was they actually came up with a matrix. And we're going to draw up that matrix here in just a second. And basically, if the terms in the first column of that matrix are positive for our transfer function here, then we can say with certainty that our system is stable. So, as we'll find, that notion will put limits on our controller gain value. So let's go ahead and try this here. To construct our Routh matrix, we have to do a couple things here. Generally goes from this works for any polynomial, and again, we're just looking at the bottom polynomial here. And so we're going to be looking at s as our polynomial term. So actually, let's first go ahead and multiply this out here. Out s plus 1 cubed plus kpkc equals, this is going to be what? Tau cubed s cubed plus 3 tau s squared plus 3 tau s plus 1 plus AP. Yeah. Yeah. Okay. This all looks right. So then for our Routh matrix here, what do we want to say? So the highest order term here is 3, and the Routh matrix by design has rows going up to our highest order plus 1. So we're going to need 4 rows here. I'm actually going to make this a little bit bigger. Oop, not that big. So 4 rows, and the first row is fairly simple. It's just going to go ahead and be the constants of our matrix here. So this is going to be the Routh matrix goes an minus 2, an minus 4 is the first row, and then an minus 1, an minus 3, an minus 5, and so on to the second row. So an, in this case, is going to be tau cubed. An minus 2 is going to be 3 tau, and then an minus 4 is going to be 0. Next, we're going to go an minus 1, that's 3 tau squared. An minus 3 is going to be 1 plus kp kc, and minus 5 is going to be 0 again. So now we get into our third row, and this becomes our b terms. So b1 is going to be equal to basically these two multiplied by each other minus these two multiplied by each other all over top of the one right above it there. So that will be 9 tau cubed minus tau cubed minus tau cubed kpkc all over 3 tau squared. Combining and kind of simplifying this a little bit, we're going to end up with 3 tau here minus 1/3 tau cubed minus, sorry, not minus 1/3 tau cubed, minus 1/3 tau minus 1/3 tau APC. So factoring out our tau here, we end up with 3 minus 1/3 minus 1/3 APAC. 3 minus 1/3, this is 9/3. That'll go to 8/3 minus 1/3. So we can go ahead and let's go ahead and pull out that over 3 term there. and make it tau over 3 times 8 minus kp kc. Okay? And that's going to be our B1 term. Tau over 3, 8 minus kp kc. Next, we have our B2 term, which is going to be this times this over this times minus this times this, all over this term. So we can see pretty clearly that that's going to be 0. And then we need our C1 term, which is going to be exactly the same algorithm as B1. So it should be this term times this term minus this term times this term all over this term. So for C1, we have tau over 3 times 8 minus kp kc times 1 plus kp kc all over tau over 3, 8 minus kp kc. Obviously, we can see that this term will cancel, and we're left with 1 plus kp kc. We could go ahead and solve for C2, but it's not really relevant to us because we don't have to keep going down the matrix. But again, for stability, what we need is we need all of the terms in this column here to be positive. So we can say tau cubed must be greater than 0, 3 tau squared must be greater than 0, tau over 3, 8 minus kpkc must be greater than 0, and 1 plus kpkc must be greater than 0. Now, tau, we know, is going to be a positive number, so these criterion are both met right off the bat here. Now, the last two, though, do give us some constraints. So, again, we know AP is going to be a positive number, so let's actually focus on that last term here first. I'm going to solve for KC and say that it has to be greater than -1 over AP. And so this is kind of one of our criterion KC, bound for it, rather, for stability purposes only. And then for our upper bound here, what we're going to go ahead and do is divide across tau over k and divide off. So we would say 8 minus kp c is greater than 0, or kc then is going to be less than 8 over kp. And so thus we've given our kc two bounds here. 8 over kp is an upper bound, and -1 over kp as a lower bound. Of course, since our kp is positive, we're never going to want our gain to be negative because it actually gives the opposite response to our system that we're looking than what we're looking for out of our controller. Okay, so let's go ahead and code this up here. We've gone ahead and imported some stuff for our from our chemical engineering library, most importantly this SymPy here, as well as a simulation function that I'll show you here in just a second. But first, let's start with our inputs. So Kp here is 12, and that's given to us. We said tau is 1.2. Our set point is u, which is 1, 2. And so then our process gain here is going to be what? It's going to be Kp divided by tau times S. That's our SIMP S there to the third power. Our controller gain is just going to be Kc, which we haven't defined, so it's going to freak out here. I'm just going to throw in a value of 1 for now. Let's actually figure out, well, we know it's upper limit. So let's type that in, 8 divided by AP, and then we'll just subtract a small value for right now. Okay, so then AC is our controller gain. Finally, we're going to want our closed loop gain function here, which we know because we derived it is going to be AP times AC. Well, let's do it in terms of gains here, just to make sure we don't really mess as much up. That's true for any closed loop. And now what we're going to go ahead and do then is go ahead and simulate here. So we're going to use this sim function. We have to go ahead and input our system as well as our step of change, u, n is going to be equal to 1,000, and we can make our dt to 0.1 here. And then that'll output for us times as well as deviation variables in terms of this needs to be a lambda t function. Lambda. Perfect. Let's go ahead and plot this up here. Equals make subplots big 2 dot add scatter x equals p, y equals our h in terms of deviation, and then mode should be lines here. Finally, let's update the layout. Template equals lovely. Let's see what we get. Okay, so again, we're right below our maximum value, right, for Kc. So this is exactly what we would expect to see in terms of the system. We have our oscillations really start to die out over time. Obviously, if we dropped our Kc value a ton, we should start to see our system approach steady state a little bit faster, right? But if we get to our upper limit, we see it go right out of control, and we have an unstable system. Even if we are right beneath the limit, it still registers unstable, right? So we got to bring it a pretty decent amount beneath that limit to start to regain some stability here and some control. So that's it for this video. We went ahead and defined stability in terms of how we could analytically find that solution for our control gain Kc based on a closed loop transfer function. That's it for this one. See you in the next one.